Hi, physics. This is just going to be a real short video here, just kind of doing it for completeness. So I have all the slides covered in the videos. Um, just a quick discussion of this very important idea that I like. So the question is, how effective are mathematics in the natural sciences? If you remember back to Physics 1, I made a big deal out of this. Turns out mathematics are unreasonably effective in the natural sciences. So yeah, this Nobel Prize winning physicist, Eugene Wigner, wrote this article that talked about this idea. And I'm so glad that he wrote this article and gave a name to this thing that is very common in physics, in the study of physics. You'll be doing a problem, and every once in a while, you get this kind of flash in your mind where it just seems really weird that this stuff actually works. You're doing algebra, you're doing calculus, you're doing differential equations, you're doing all this really bizarre math. It all seems very abstract, and yet it perfectly describes the universe. It does so unreasonably well. It's very bizarre. So, what the hell? I'll read the quote. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. So I think that's the very end of that article. If not, it's near the end. But yeah, the strange idea that math actually describes the universe very, very well, and we don't really know why. And occasionally, when you're doing this stuff, you might get that idea pop in your head. Why does this actually work so well? It's bizarre. So, when you're doing high school physics, you'll do some physics, you'll set up a math problem, and then you'll do the math problem. And typically, that won't involve any math beyond the level of algebra. So when we were analyzing these circuits here, that's what we did. Took this complicated thing, drew our currents, named them. We named them all. We drew our loops. We used our loops to build a system of equations, and then we solved the system of equations. Just algebra. And yet it perfectly describes a real physical thing that could happen. If you actually built this circuit and did all this work, that's what you would get. So yeah, when you're doing this in high school, it doesn't really go further than algebra, really. When you're doing it in college, it's the same basic idea. You're going to use these physical ideas. You're going to create a math problem for yourself, and then you're going to solve it. Only you're going to have to use more than algebra. You're going to have to use the more advanced things: calculus, linear algebra, which is solving systems of equations in a more abstract way, differential equations, and all kinds of bizarre things. So same basic idea, set up the problem and then do the math. It's just that the math gets really weird. So for example, if you're taking electronics in college, you may have to do the same exact kind of thing that we just did in the last problem. Only instead of having two loops and just batteries and resistors, you're also going to have capacitors, and you're going to have these things called inductors. And instead of having batteries, your voltage sources will be alternating current. So they'll be varying sinusoidally. And so it's written here in this notation where the angle, it's giving you, what is it called? Phase lag. They're offset by a different angle, which represents a time. It gets weird. But yeah, you might do this, and you'll notice there's all these J's in these problems. These lowercase J's, what do they stand for? They're actually the square root of -1. Sometimes when you're doing electronics, instead of using little I, because I sometimes I is current, sometimes you use little I for partial currents. So yeah, when you're doing electronics, they tend to prefer using lowercase j as the square root of -1. So you can imagine how difficult it would be to build a system of equations and then do all the substitution and elimination stuff if your coefficients, instead of being real numbers, ended up being complex numbers. So they have a real and a complex part. It is, if you get to do it. It's tricky, it's tedious, it's annoying, but it is the same basic idea. So that's it for this video.